All right, let's talk about braking. Ever wonder what's really happening when you hit that pedal hard? It's so much more than just slowing down. It's actually this incredible dance of physics, and understanding it is key to understanding why cars behave the way they do. You've definitely felt this. You brake hard and the whole front end of the car just dips down. It's a universal feeling for any driver. But if you ever stop to ask, why does it do that? What is actually going on under the skin of the car? Now, the common explanation you'll hear is that the weight moves forward. And, it feels like that's what's happening. But from a physics standpoint, that's not quite right. The actual mass of your car isn't shifting. What's changing is how that mass is distributed onto the tires. The correct engineering term for this is longitudinal load transfer. It's all about the dynamic redistribution of the vertical load pushing down on the front and rear tires. So let's break down exactly how that works. First up, let's really deconstruct that familiar nosedive when you brake. And to do that, we have to go back to basics. I'm talking about Isaac Newton's first law of motion. Yep, it all starts with inertia. An object in motion wants to stay in motion. Simple as that. Okay, look at this diagram. It shows you exactly what's happening. You've got inertia, which is trying to keep the car's center of gravity, that point high up off the road, moving forward. But at the same time, the braking forces are acting way down low at the tire contact patches. This difference in height creates a lever, a rotational force, and that's what physically pushes the nose down and lifts the rear up. So how can we actually quantify this? Well, let's get into the physics. The cool thing is, this isn't just a vague feeling. It's a completely predictable event, and it's governed by a very specific formula. Understanding this is absolutely fundamental to vehicle design. And here it is. The amount of load transferred is equal to the car's mass times its deceleration times the height of its center of gravity. All of that divided by the wheelbase. Now, the key thing to notice here is what's on top and what's on the bottom of that equation. A higher center of gravity means more load transfer. A longer wheelbase means less. That relationship is critical. And this chart shows you exactly how that plays out in the real world. Think about an SUV. It has a high center of gravity and a relatively short wheelbase. So what happens? You get a lot of load transfer and a very noticeable nosedive. Now compare that to a sedan, which is lower and longer. Much less load transfer, much less dive. It's that formula in action. Okay, so you might be thinking, more load on the front tires means more grip, right? And you'd be correct. But it's not that simple. It actually leads to a really interesting paradox. This is a concept called tire load sensitivity. The thing about tires is they're not perfectly efficient. Yes, adding more vertical load does increase grip, but you get diminishing returns. Doubling the load on a tire does not double its available grip. So here's the kicker. The front tires are gaining load and gaining grip, but they're doing it inefficiently. At the same time, the rear tires are losing a ton of load and therefore a ton of grip. When you add it all up, the vehicle's total potential grip is actually lower during hard braking than when it's just cruising along. So if the front tires are doing most of the work anyway, why does this matter? What's the downside? Well, the problem is balance. A huge imbalance of grip between the front and rear axle is a recipe for instability, and that's something engineers work incredibly hard to manage. So that brings us to the solutions. Let's look at how engineers actually design cars to control these powerful forces. But before we do, we have to get one thing crystal clear, because this is a common point of confusion. Load transfer is not the same thing as body dive. They're related, but they are two distinct phenomena. Think of it this way. Load transfer is the invisible, instantaneous shift of forces. It's pure physics. It would happen even if a car had a completely solid, rigid suspension. Body dive is the visible result of that transfer. It's what you see and feel as the suspension actually compresses under that new, heavier load. Okay, so how do they manage it? Well, there are a few key strategies. First is brake bias. They literally make the front brakes bigger and more powerful to handle that extra load. Second is anti-dive geometry, where they angle the suspension components in a clever way that uses the braking forces to physically resist that nosedive. And on modern cars, you have electronic brake force distribution, which constantly adjusts brake pressure to keep those lightly loaded rear wheels from locking up. So let's bring it all together. Why is understanding all this so incredibly important? This table is a perfect summary. Let's walk through it. The front tires get more load, which means more grip. But if they're overloaded, you get understeer. The rear tires lose load, making them prone to locking up, which can cause oversteer. the front brakes have to work way harder and deal with more heat, and the whole chassis pitches forward, which messes with the car's aerodynamics and even its steering. It's a total chain reaction. So you can see, this isn't just some abstract concept. It affects absolutely everything about a car's performance and safety, from how the brakes are designed, to tire wear, to how a race car is set up for a specific track. It is foundational to vehicle engineering. And that leaves us with one final thought. We've established that the amount of load transfer changes depending on how hard you brake. So, with all of that in mind, why do you think a professional race car needs to have brake bias that the driver can adjust right there from the cockpit, sometimes even from one corner to the next?